In this video, we are going to continue discussing a line integral through a conservative vector field. We have this vector field that's there from A to B. And we are going to check first to see if it's conservative. So we have M, N, and P. So we're going to take the derivative of N with respect to X. All right, so we get Z squared. Then we take the derivative of M. First, let's write out our equalities, actually. Partial of M with respect to Y. And then I'm going to do N with P now. So that'll be a Z here. And a Y. And then another vector here. This is just going to be M and P. That's the last one that we have not done. So we'll put a Z here. Then we'll put a P with an X. We have to confirm all three of those equalities to show conservativeness. So N with respect to X is going to be Z squared. M with respect to Y is Z squared. So we're good on that first one. The second one, N with respect to Z is 2xZ. P with respect to Y, the Y just goes away. I get 2xZ. We're good there. And then the last equality that we're checking, M with respect to Z is 2yz. P with respect to X is 2yz. All right, so we have shown that the vector field is conservative. All right, so that means we can use the method from the section. So that means there is a phi that is equal, if I take the gradient, it's equal to f. That means I can think of f as the gradient, which is the derivative of phi with respect to x, derivative of phi with respect to y. And then we know this is equal to, we got to do our z portion, phi with respect to z. And this is equal to M, N, P. So we're going to work backwards from that. So phi of x, y, z is equal to the integral of phi with respect to x dx, which is the integral of m dx. We can go ahead and replace that with m, which is yz squared. All right, we have to integrate that with respect to x. Notice it's kind of nice. There is no x. So I just introduce one. And then now I have a function that's in terms of y and z. So I like to rewrite it here. Then phi of x, y, z is x, y, z squared plus h, y, z. So that's a function of h in terms of y and z. Now I'm going to take the derivative. So the derivative of phi with respect to y, all right, the y just goes away. I get x z squared plus h, I don't like to write that with the prime, partial phi, not phi, h with respect to y. There we go. And then I'm going to set this equal to, we just did y, remember that is the same thing as n. Let's see what n was. N is x z squared. All right, that tells me that h, or the partial of h with respect to y is equal to 0, which tells me that h of yz is equal to, well, if it's 0, we got to do a constant, but it's not a normal constant. It's going to be in terms of z. All right, so then I'm going to rewrite phi now. Phi of x, y, z is equal to x, y, z squared plus, and then we just said that h, y, z is just g of z. We had a constant. That's all that came out of that. Now, I do that same thing. So I take the derivative of this thing with respect to x now, or z, sorry. Thinking the right thing, said the wrong thing. Z, I get 2xy z plus g prime of z. And we're going to set this equal to p, because that's the one that is phi derivative with respect to z. Right, p was equal to 2xyz. Surprise, right? That thing goes away. Which tells me that g prime of z is equal to 0, which tells me that g of z is just a constant c. Thus, now we have phi, x, y, z, equals x, y, z squared plus c. Now we can use that fundamental theorem. The line integral of c over the vector field times dr is equal to phi of, and we just plug our points in. The 2 points, I have them here in my notes, is 1, 3, 2 minus phi of 0, 0, 1. And that's going to end up with a nice pretty 12. Alright, so you can see this method is very repetitive. I said it towards the beginning, I think, of these videos, it's kind of a follow your nose thing. It's just one integral, and then you take the derivative to get the next next derivative of my gradient, and then I take an integral, and then I take the derivative of the next part of my gradient, until you get all the way down to that there's no more of these functions like this. Get some repetition under your belt. I promise these get easier with time. So